Okay, welcome back everyone to the part 2 of linear subspaces. So today we're going to look at some examples of linear subspaces or some counterexamples of linear subspaces. So that's what we're going to do today. So yeah, let's just get right into it. So we can actually start off with a very simple one, an exceedingly simple one, which would be, let's take the set, let's take the set S. I usually denote sets by using S. I might change that in within the next few minutes. But let's say this set is equal to, so we have a set that contains only the zero vector in 2 dimensions. Right? So this is a very basic set. So now we can actually just check to see if this is a subspace of some kind of set. We can say, is this, actually I'm gonna abbreviate this a bit or make it shorter. Subspace of R2. So we're asking for this one. This is subspace, and you actually, this is just going to be a general question. This is just going to be a general question throughout the video. So I'll just put Rn, so any dimension of the reals. Okay. So is this a subspace of Rn? Well, we can go through a checklist. Our checklist can be here. I don't want to make this in a box because you can actually use this as a checklist. Right. So hope you can see that. Okay. So does it include the zero vector? Well, it does. The zero vector is the only vector within the set, or value within the set. So this is going to be a check. This is going to be a check, right? Is it closed under multiplication? Well, let's see. If you multiply any constant in R2 in this case, if you multiply any value in the reals, right, then what you'll get is, well, any constant C1 times the zero vector in 2 dimensions is just going to be equal to the zero vector in 2 dimensions, right? So it is in fact closed under multiplication. So we'll put a bold check mark there. Now let's see, is it closed under addition? Well, this is obviously fairly obvious, but this might give you a bit of an intuition on the process. Well, is it closed under addition? Well, the only way of adding this vector is by adding it to itself, and the zero vector in 2 dimensions, that's not the square, it's just the zero vector in 2 dimensions, is just equal to the zero vector in 2 dimensions, right? So it is in fact closed under addition as well. Alright, so that was our first example. We can just make a big check mark with this. Alright, let's get rid of these check marks here. Let's see. Okay, so this is our first example. Let's take a look at a little more complicated example, and hopefully this will exercise your notation in linear algebra. So let's say this was just set 1. so we can use this more often. Let's look at set 2. So this is our second set. And don't get this confused with the integral sign or the antiderivative sign. I'm sorry for my S's, but I can bold it a bit just so it's a bit different. Okay. Well, S2 we can set this equal to, we'll have some parameters here. We can set this equal to, let's just say all the values 1, 2, 3. Let me actually include. Actually, no. This is going to be different. Okay. 4. Right. So. Oh, sorry. Such that, or for which, such that, let's say our n, where n is any of these values here, put n here, such that n, let me see if you can see that, I'll write it over clearly, n, such that a value of n is such that n is member of the reals, right? N is a member of the reals for n is somewhere between 1 all the way between, actually, it can't equal infinity, so you have to write it like this. So that is our set here. So it's our set with all these values here, such that n is a member of the reals for n is between 1 and between infinity. Okay, so obviously the set goes on forever. Okay. So anything else I could add to this? Okay, nothing else. So this we can think of this set as our natural numbers. So the set we can think of that as our natural numbers. And we're essentially asking now, is this set a member of the reals? Is this set the natural numbers, not including 0, I must add. So I can actually add another parameter that n cannot, I actually already added the parameter here. Okay, so would n be, I'll, just to make this clear, I'll set this equal to natural numbers. Okay. So what we want to see is n a subspace? So let's mark it off here. Does it include the 0 vector? Well, we already see that n does not include the 0 vector because obviously even if this is 1D, it only gives the magnitudes of these values. We can easily see that one is that given this parameter, it can't equal 0. In other words, the 0 vector. So in other words, we can actually just write down. We can actually just say that. Let me erase this better. We can cross out includes the 0 vector easily, right? Okay. Well, we already know that it's not a subspace, linear subspace, but we'll just check the other options just for practice. So is it closed on multiplication? Well, intuitively it should be, right? Because if you take any value here, we'll call, I don't know, we'll call some random values here. So we'll have, let's see, what could we use? A and B, that's the best way. A and B are members of the set the set here, right? They're a member of this of the natural numbers. Okay, so now if it's closed under multiplication, why did I say it's pretty obvious that it is? Well, it's obviously not, because if we take any values, so any constant multiplied by, actually I don't want to add both A and B to be in the reals. So A can be a member of the natural numbers, here not including 0, and B is a member of the reals, right? I have to actually edit this because it's not a member of the reals in this case. So, oh well, it is a member of the reals. Not bad. N is a member of the reals. For just rewriting this. Okay. So if this is only a member of the reals, this is only a member of the set here. If we say that B, B can equal, square root 2 E pi, etc. And if we say that an A can equal 1, 2, 3, etc. And if you multiply A by one of these values, like pi, well, then it becomes irrational and it's not a member of the set anymore. So it's obviously not. So obviously there are some exceptions, which I would like to add. For example, one obvious exception would be, because we can't just state that if we find the product of A and B, we can't just say that that's not equal to we can't just say that that's not a member of the natural numbers, because there are some exceptions. Like I said, there are infinitely many exceptions, but an obvious one would be if we say that if we take 1 over A, or if we take A, which is obviously just some random number of the natural numbers. So, example, if we take 1 over A, and let's take A first, just to divide by this, even though it's obviously commutative, but just to make things more direct. So let's say A here, and then we take the product A and B, and let's say B is equal to 1 over A. And that's fine, right? If we say that A is equal to 2, 1 over A is just a rational number, and rational numbers are a subset of the reals. So, however, 1 over A is not a member, of course, unless A is equal to 1. It's also another exception. But if we take the product of this, we will always get 1. This is the identity of this, right? And 1 is obviously a member of the natural numbers here. Okay. So that was our example. Feels bad to erase all of this, but I like seeing a filled board. But I need to work high up here, so. going to get some more room. So this is our second example. This is not subspace. Oh, and I also forgot to ask if it's closed under addition. Well, this is even more obvious. If you add any of these values, we will say n or a, because that's what we used beforehand. Obviously, a is a member of natural numbers. Okay, and a and b is also a member of the natural numbers. And let's say if we take a plus b, if we take a plus b, it will always be, or I can actually write it like this. So it will always be greater than 1, right? Because since we don't have rational numbers, or since we don't have some of the rational numbers, like 1/2, we can't say that it's greater than, or we can actually, we can't say that it's greater than or equal to 1, or greater than or equal to 0. But that would get the point across nevertheless. So, yeah. Okay, so this basically shows that, well, it is closed under addition because, that's one of the examples. That's just saying that it's always positive. That's the point there. But also because, we don't have any, just intuitively that's the case. But the only way that we could conceptualize actually not getting, leaving our set here would be for there to be, would be for these to add up to a negative number, which they can't, because all our values here are always positive. So that's why this is closed under addition, right? So we can X this out and check that. Going to get rid of this. Okay. I wonder what the time is at the moment, but I'll just continue here. So let's see. What could be our last example? Well, this would be the most exciting one, the most interesting one in my opinion. Let's find this one. So since this isn't any specific set, we can call this S2. Let's say this is a set of all ordered two tuples. We've talked about this in the past. So x1, x2, such that, let's put some parameters here, such that firstly, xi's are members of, so in other words, x1 and x2 are members of the real values for the fact that x1, or we can use either one, but let's see, we can say that for x1 is greater than or equal to 0. Okay, so that's our only parameter. Those are only parameters here. I know I'm writing a bit slanted, but it's kind of difficult here for me. So that's how I'm going to do it here. Okay, so now we're asking, is this a subspace, right? Well, taking the first glance at it, it's kind of jargony in a poetic sense. But when you graph it, when somewhat graph it, get a visualization of what it means, it gets more intuitive. In other words, you can visualize whether this is a subspace or not. And again, we're asking if this is a subspace of R2. Alright, so let's quickly graph this. So we have our 2D coordinate axes. So basically R2 would just be It looks like a diagonal. Hold on, let me redo this. My bad. R2 would just be all of this. No, I'm not drawing any graph. This isn't a function. This is, I've never done this before. I've never been in front of a board like this, so pardon me. I just need to find a good strategy for this. All right, so that is R2, right? But what is this subset here, this graph here? Well, x is greater than or equal to 0, so we can say that it's greater than or equal to 0, and x1 is our x component, so thus it can never go past this area. So, and our y value doesn't matter, so we're assuming that it can be positive or negative. So it would just be that all of this area. So just this half. Obviously this is continuous. All right. And this is our set S2. Okay, so now with this visualization, let's try going through this checklist. Obviously this does include all of this, since obviously the origin, this can be greater than or equal to 0, so we do have the 0 vector, and that leads us right through this here, and obviously the y value doesn't matter, so it can be negative or positive. Alright, so I think I'm going to do part 3 on this, by the way. I don't want to make this video too long. So let me get rid of this. So let's see if I'm going to try experimenting with different colors here, just to make things more clear. So it doesn't include the 0 vector, where we just saw that it includes the vertical axis or the y-axis. So we can check this off. Okay. Is it closed under multiplication? Well, that's where this falters. Okay, now that sounded a bit over exaggerated compared to our other examples. But is it closed under multiplication? Well, let's check. So let's say we have a vector here. We have a vector in S2. And let's say we have a vector here, vector 1, which is equal to, say, A, B, generally here. Okay, so we have a vector 1, which is AB, so that's just general definition here. And then we have a vector here in R2 in general. We're going R2. And obviously B can be positive or negative, and A can be R2. Oh, why did I write R here again? Okay. We have vector V2, which is equal to and let's say we have positive A and well, it's okay. Okay, I'm not gonna meddle with that too much. And then actually I'm gonna write that a little less slanted because that's a little too slanted. So we have vector V2, which is equal to CD. All right. Well, we have this. And is it closed under multiplication? Actually, we'll deal with this with addition. But let's say that we take a component vector V2, and if we multiply or actually we can still use this example. Let's see if C is equal to, or C is less than 0, because it can, since the reals include negatives as well, obviously, and this includes this entire line here, or integers in other words. So C, that's very wrong. C is less than 0. All right, so let's say that C is less than 0. Okay, C is less than 0, and obviously D, we don't have to set any parameters for D, because the value of D really doesn't matter here. And let's say that A obviously has to be greater than or equal to 0. Okay. And if that's the case, then if we multiply these two, then unfortunately what we get is either 0, which lines up, so we'll actually just say it's only greater than 0. Unfortunately, what we get is a negative value, right? So that means it's not part of the set. So in other words, it's not closed under multiplication. So we X that out. Is it closed under addition? Let's see. So we have our vector. We're going to reintroduce our vectors. We have v1, which is a b, and v2, which is c d. All right, and let's sum. Or actually, these should be in the same set now. So I'm going to say that. I'm not going to confuse you, so I'm going to reintroduce a new vector. We'll use the same notation, but just remember that we're using different vectors. These are unrelated than the last example. So these are CD, and they're both members of our set. That's 2. Okay. All right, so we can write it as v1, v2 are a member of our set S2. Okay, I'm just going to double check to see if you can see everything. All right. So we have this, and if we add the two equations, well, we know that A and C are both greater than or equal to 0, and B, D we have two possibilities here. Can both be greater than or equal to 0, or B and D can be less than or equal to 0. Or we can just simplify that by doing that. We'll just write it like that just to simplify. So we have these two possibilities. These two are combined with these. Okay. So we can tell that if we sum the two, which are both a member of the set here, if we sum the two, then obviously, if we sum the two, we'll get. I'll write this out, and this has nothing related to R2. I'm gonna write with purple because it's a little easier to see. So if we sum v1 and v2, vector v1 and v2, we get A plus C and then B plus D. I've given this example a few times before, and like I said, we know that A and C are both positive, so this result will be positive, And we don't even have to worry about this section here, right? This section can be either positive or negative, and we know that both of these values have to remain in this side of the coordinate axis, so we don't have to worry about them being irrational or something, or fractions, right? So we can easily say that this is in fact closed under addition. So nevertheless, we still know now that this is not a subspace. So hopefully you enjoyed that video. Hopefully it was a bit more organized than the last video. Last video was, like I said, it was just practice. I'll gradually be getting better at this style. I'll switch over from style to style on my iPad, from my iPad for that matter. Maybe even going back to the paper and marker. And obviously this style as well. So hopefully you enjoyed, and I'll see you soon with the part 3. And bye.